All right, hello everyone. In this video, I'm going to talk about diagonalizations. This is the one of the series, one video series of singular value decomposition (SVD). Okay, so all right, let's see. What's a diagonalization? Diagonalization is the one of the way to factorize the matrix. Okay, so let's see. If A can be defactorized as the P times D times P inverse, so here's D's diagonal matrix. Okay, so we wanna de-investigate this one. A is equal to P times D times P inverse. Okay, so but here's a question: why factorization matters? Because factorization makes the easy to compute the a to the case power. Okay, so let's see example. The D example one is the matrix D is a 2 by 2 matrix, and then especially D is a diagonal matrix. A diagonal matrix is the diagonal and only diagonal entries are non-zeros, and all other entries are zero. Okay, so this is diagonal matrix, right? Then we want to compute the d times d, I mean d square through the d to the k's power. As you can see that the square is a square 0 and 0 and b square. All of the non-diagonal entry is 0, and then diagonal entry just take a square, right? And then similarly, we see the d to the k's power is like this. So we see the pattern, right? So it's easy to compute the d to the matrix k's power if matrix is diagonal matrix, right? So what about the the square matrix, any square matrix? So let's see, A is a 2 by 2 matrix. Okay, so if we can factorize A as P times D times P inverse, so where P is like this and D is this one. Okay, and since P is a 2 by 2 matrix, it's not a big deal to find out the P inverse. So yeah, let's see right here. So we find the determinant, and then uh, you know the swap the 1 and -2, and then put the negative sign in the other entry. So all right, so now let's find out a square. Let's compute the a square. Then since we express a as P times D times P inverse, okay, so then there's a square here. There's miss the square. It's equals 2. Okay, I missed that. Sorry. Then we got this P D P inverse and P and D and P inverse, and then apply the associative the property. Then we compute the P inverse P first. That's going to be identity matrix, right? And so we got P D square and P the inverse. And then what about a third power is a square. So similarly, what we did here, we do we compute the P inverse and P first. Then we got this. So now you see the pattern, right? So then a to the k's power is equal to P times D to the k's power times P inverse, right? So now then the that is, A is equal to P D P inverse if A can be factorized as P D P inverse. That is called the diagonalizable. Okay, so a square matrix A is said to be diagonalizable if A is similar to the diagonal matrix. Similar to diagonal matrix means that A is can be expressed as P D P inverse. Okay, so here's a theorem, diagonalization theorem. So let's see this one. M by M matrix A is diagonalizable if and only if the IFF stand for if and only if. Okay, so A has n linearly independent eigenvectors. A has not just n n eigenvectors, but these n eigenvectors are linearly independent. Okay, so what does that mean? So since A, you see, A is diagonalizable means that A can be factorized as a PDP inverse. Okay, so you see that right here. Okay, and all the diagonal entries are actually it turns out that these are just eigenvalues, and then the columns of matrix P are it turns out that eigenvectors corresponding to these eigenvalues, which are diagonal entries of matrix D. And then these eigenvectors, I mean the columns of matrix P, are not just the eigenvectors, but linearly independent eigenvectors. So these are linearly independent eigenvectors. So we can say that V1 through Vn are actually eigenvector bases of Rn space. Okay, so V1 through Vn are linearly independent eigenvectors corresponding to the eigenvalues lambda 1 through lambda n of matrix A. And that means, those eigenvectors, I mean V1 through Vn columns of matrix P, actually eigenvector basis of Rn space. Okay, so then so let's prove this. Okay, so since the how to prove that theorem, so we're gonna assume that A is diagonalizable, so that A can be expressed as PDP inverse, and then we show that A has n linearly independent eigenvectors. I mean, those columns V1 through Vn of matrix P are actually linearly independent eigenvectors. Okay, and then the other side, we assume that A has n linearly independent eigenvectors, and then we show that A is diagonalizable. Okay, it means that A can be expressed as PDP inverse. Okay, so we have to prove 2A. So first one, okay, so for any matrix P, n by n matrix P, and then any diagonal matrix D, okay, then A times P can be expressed as like this: AV1, AV2, AVN, right? Okay, so I hope that you are familiar with the matrix operations. Okay, so this, by the basic matrix operations, we can express AP as like this. And then P times D is also what? Since D is diagonal matrix, so matrix times the diagonal matrix is nothing but what? The diagonal entry times the column vector of the matrix P. So we can say it. Okay. All right. So that's the kind of the background of the proof. Before we start the proof, we just to figure out the the matrix form of AP and PD. Okay. So now we prove here we assume that A is diagonalizable, means that A is PDP inverse. Okay. All right. So now then, since the PDP inverse, so we multiply by P on right multiply. Okay, we just apply right multiply by P on this region. Okay, then we're gonna get AP times PD. Okay, but we use that expression for AP, and we're gonna use this expression for PD. Okay, so by 1 and 2, then we got this AV1 through the AVN, and then lambda 1 times V1 through lambda n Vn, right? So those two matrices are equal. It means that each pair of the columns must be equal, right? So we equating columns, we find that AV1 is equal to lambda n V1 through the AVN is equal to lambda n Vn, right? Okay. So now then, the P is invertible, right? Because so we assume the A is diagonalizable. It means that there exists matrix P, and then that P is inverse, has an inverse matrix, CP inverse. So we assume that. So P has inverse matrix, means that P is invertible. It means that V1 through Vn must be linearly independent. Okay, and then we say all of the column vectors must be non-zero, otherwise not going to be linearly independent. So now then V1 through Vn are linearly independent eigenvectors. So we see the AV1, the lambda V1, that means what? V1 must be eigenvector corresponding to lambda 1, right? Okay, so from there we can say that V1 through Vn are eigenvectors of matrix A corresponding to eigenvalues lambda 1 through lambda n, but since P is invertible, So all of the eigenvectors v1 through vn, that means actually columns of matrix P, right? But anyway, so v1 through vn are linearly independent as well. Okay, so proof is done. Okay, and then the other way. So suppose that A has n linearly independent eigenvectors. Okay, then we're gonna use them, that linearly independent eigenvectors. We construct the matrix P. Okay, so v1 through vn are what? Linearly independent eigenvectors. Because we suppose that, we assume that A has n linearly independent eigenvectors. Use them to construct the matrix P. Okay, whose columns are linearly eigenvectors of matrix A. Okay, and then the second one, we're gonna use, then since we assume that A has a linearly independent eigenvectors, so this is eigenvectors. That means there exists corresponding eigenvalues, right? So we're gonna use corresponding eigenvalues lambda 1 through lambda n to construct the matrix D, diagonal matrix D, and then use the 1 through 3. See that 1 to that expressions, and then this one, then we can say AP is PD, right? And then V1, V through Vn are linearly independent. That's assumption, right? Okay. So what we want to show? That we want to show that A is diagonalizable. It means that A can be factorized as PD P inverse. Okay. So anyway, so V1 through Vn are linearly independent. It means that P is invertible. Okay. So if you don't get it, just please look at the invertible matrix theorems. Okay. So then, so APPD implies that what A is equal to PDP inverse. I mean, simply we multiply, the right multiply by P inverse this relation, so we got this. So it means that A is diagonalizable. Okay, so I prove it's done. Right. So that's the today we saw the diagonalization theorems. Okay, so that's for today.